The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hi, and welcome to Skeptically Speaking. I'm Marie-Claire Shanahan, guest host today for Desiree Shell. This week, we're looking at the fascinating insights that applied math can give us about how science happens, how people communicate facts, and even a bit about how our brains work. A little later, I'll be speaking with Mark Daley, a computer scientist at the University of Western Ontario, about how he uses computational modeling to understand gene networks, languages, and even musical compositions. But first, I'm really pleased to be joined by Samuel Arbesman. Samuel is an applied mathematician and network scientist. He's a research fellow at the Institute for Quantitative Social Science at Harvard and senior scholar in research policy at the Ewing Marion Kauffman Foundation. His first book was released in 2012, The Half-Life of Facts: How Everything We Know Has an Expiration Date. Welcome, Samuel. It's a great pleasure to speak with you today.
Thanks so much. Thanks for having me on the show.
So let's really start from the broad. Tell me what you mean by saying that facts have a half-life.
When we think about facts, or I'm using facts as a fairly general term to mean like bits of information and knowledge that we have in our heads, we often either think of facts as entirely unchanging or little things that we think are true and then we find out that they're no longer true. So for example, what foods are unhealthy for us? This kind of thing, we read something in the newspaper, then we read the exact opposite the next day, or we read things about what we think we know about science, such as what dinosaurs look like. We used to think they were these like big gray-green reptilian monsters, and now they look more like fearsome chickens. There's all these different things that are changing. But the idea with the half-life is that I'm using the analogy from physics. So in radioactivity, when you have a single atom of a radioactive material, you can't predict when it's going to decay. We know exactly like when it will, or if it decays, what that decay will look like, but we can't predict when that decay will occur for a single atom. That's unpredictable. But things change when we get a whole bunch of radioactive atoms together. You get an entire chunk of uranium, for example. Then we can trace out a curve of decay, and we can even describe it with a single number, the half-life. And I'm trying to make the same kind of analogy with knowledge. We can't predict which specific discovery is going to occur or which fact is going to be overturned when we learn something more. But the idea is that in the aggregate, knowledge is far from random. There's a shape to how knowledge grows and changes and even becomes overturned, and you can use math, similar to the half-life, to actually understand how knowledge grows and changes.
It's a really great analogy. But are ideas and facts really that as predictable as radioactive materials? Can you give us an example, maybe?
Probably by and large, they're not quite as predictable, but there are regularities. So there was a guy, Derek J. DeSola Price. This is back in the late 1940s. He's considered like one of the founders of the field of scientometrics, which is like the science of science, quantitatively measuring science. He had recently become an instructor at Raffles College, what's now the National University of Singapore. And when he got there, the library was being renovated. And I guess the library was pretty small, so they were giving out all the volumes to store to students and faculty while the library was being fixed. So Price got this complete set of a British scientific journal and brought it home. And he was looking at the heights of the piles, and the piles were chronologically ordered and stacked against the walls in his apartment. And he noticed that there was actually a mathematical shape to the height of each successive pile. And so he began to collect more and more data, and he realized that it turns out, by and large, there are these clear regularities, whether it's exponential growth or other clear mathematical curves, to how knowledge grows. So whether or not you're looking at the number of articles in science, the number of journals within science, how the number of elements in the periodic table that have been discovered grow over time, even the number of universities over time. These all obey clear mathematical regularities. And it turns out, just as you can measure the regularities, you can also actually measure how knowledge becomes overturned. So this is about, I think, a little more than a decade ago, a team of scientists in France, they wanted to measure how knowledge becomes overturned in two medical fields. It was hepatitis and cirrhosis. These are both related to diseases of the liver. So they gave a series of papers to a panel of experts, and these are papers from, I think, a span of 50 years. And they said, which of these papers are true, and which ones have been overturned or otherwise rendered obsolete in some way. And from that, they were able to actually trace out a clear curve of decay. And they found from this clear curve of decay, you could read off the sort of metaphorical half-life of knowledge in these fields. In this case, it was about 45 years. It took about 45 years for the knowledge in these fields to become overturned or otherwise rendered obsolete. And it turns out you can do either using an actual panel of experts or a proxy of how long it takes for papers to stop accruing citations or references from one paper to another. And from that, you can actually figure out how long it takes for knowledge to become overturned or no longer part of the living scientific conversation. And there are real mathematical regularities behind it, which is pretty exciting.
Yeah, that's really cool. And as you say, it's not so much being able to predict which specific facts, but the idea that I guess half of them in a particular amount of time, by the time that time has gone by, about half of them will have become outdated. Is that right?
It's a little bit messier than that. Sometimes you can't actually fit like an exponential curve or exponential decay. Sometimes you can fit other kinds of curves. Oftentimes it's a little bit messier. But by and large, you're right. You can't predict specific discoveries or specific things that are going to be overturned necessarily. But you can say, okay, in the aggregate, there's a shape to how knowledge gets overturned and changes over time, which is quite astonishing.
It really is, because it feels a little bit like these things happen in fits and starts and would to a certain degree be random, not just on the individual level, but even in the aggregate.
Yeah, and I think that's the kind of thing that even though there might be a certain of randomness or stochasticity, if you can recognize the patterns underlying this, then you can actually chart out curves of change, whether or not it's like these curves of growth, the curves of overturning of knowledge and this churn. But there are really regularities. I mean, similar to the radioactive material. Even though we can't predict when a specific atom is going to decay, there are certain trends. And when you have a large enough number of atoms, these trends become clear. And the same kind of thing can be done with knowledge.
It's a pretty cool way to look at it. And all that, in a way, starting from somebody stacking up journals in their room.
Yeah, it was good that he noticed it because that and coupled with him having, I think, a whole bunch of students that could collect a lot of data, because this is in the age before all the information was digitized. So he needed to have a lot of students and be able to recognize very interesting things.
A lot of students always helps, I think.
Yes, that is true.
So you mentioned that you take the term fact kind of broadly, and you introduce a really interesting term for a particular kind of fact that is somewhat long-lived, but not entirely eternal, I guess is a good way to say it. Can you tell me a little bit about those?
So at one point I was thinking about the rate at which facts change. So on one hand, we have facts that change really quickly. So these are facts like what the stock market closed at yesterday or what the weather is going to be like tomorrow. These are the facts about the state of the world, and they change really rapidly, and we're prepared for this. On the other extreme, we have facts, bits of information that change really slowly or effectively never, like how many continents there are on the earth or how many fingers there are on the human hand. You learn these facts once. When you're young, you don't have to worry about them changing. But in between are what I term mesofacts. These are facts that change on the meso or middle time scale, facts that change on the order of a year or decades, or essentially on the order of a human lifetime. And these facts actually encompass a lot of what we know. And so like it can be everything from how we take care of babies, so whether or not babies should sleep on their stomachs or their backs, or other bits of information, facts about other aspects of scientific knowledge, facts about the state of the world, such as how many billions of people there are on the planet. We recently hit 7 billion. I think I learned 5 billion when I was in school. My grandfather, he learned less than 2 billion, if not less than 1 billion. And even facts about like technological change, like how we store information. We've gone from like the big floppy disks to the smaller floppy disks to CDs to DVDs. We live in the cloud. There was like that zip disk era in the early 2000s. And so there are different types of knowledge. There could be facts about the state of the world, facts about things that we think we know in terms of scientific knowledge, but it turns out all these different types of facts often change in similar ways. And one of the ways we can think about them is the rate at which they change. In this case, all these facts are mesofacts. They change on the order of human lifetime. And the problem is, though, we learn these facts when we're young, when we're informational generalists, alongside all the facts that don't change effectively at all, or change really, really slowly, far longer than over the course of a single lifetime. And then as we grow older, we specialize. We learn more and more about less and less. And unless those facts that are changing are in our area of specialty, we don't realize that these facts are changing, and we neglect to update it, often until our kid comes home and says, guess what? Dinosaurs are warm-blooded and have feathers, or some other fact. And so dealing with mesofacts is a very important problem. It's a big problem because we learn a lot when we're young, and then neglect to change or recognize that these things change.
You use a brontosaurus as a pretty good example.
Yeah, and we used to think, and I grew up learning about the Brontosaurus. I actually have a book that was written. So there was a thing, it was a really cool project when I was in kindergarten. They paired each kindergartner with an eighth grader, and the kindergartner would talk to the eighth grader and about what they were interested in, and the eighth grader would go and make a book about the things that the kindergartner was interested in. So when I was in kindergarten, the eighth grader I was paired with made a book about Dr. Sam Arbesman, the paleontologist, going to, I think, South America to find a Brontosaurus, which was really cool. And so because I love dinosaurs. The problem is, it turns out the Brontosaurus really doesn't exist anymore. It never actually existed. It had to do with a misclassification and putting the wrong skull on the body of another dinosaur. We now call it the Apatosaurus. That's the correct term because it has priority. There's many people who actually feel that Brontosaurus is probably a pretty good term as well, even within like scientific nomenclature. The problem is the shape of the Brontosaurus, what the Brontosaurus looked like, its head and how it looked, that doesn't actually exist. That's not a real dinosaur. And for many people, this incorrect bit of knowledge is still in people's heads. And so there's actually a great book that just came out by Brian Switek called My Beloved Brontosaurus. And it's all about the new knowledge about dinosaurs and how our dinosaur knowledge is changing over time. And when I was actually writing this part about the Brontosaurus, I spoke for a long time with Brian, and we both commiserated in our love for this now vanished creature. Dinosaurs are all now vanished, but this creature never even existed.
Yes, even our toys of it that I had one too, and I don't know why, but I think if you weren't into ferocious dinosaurs, I think it was a lot of people's favorite. It seemed very placid and gentle. I don't know.
Yeah, I think probably if you watched like Land Before Time, that was like one of the main characters.
That's true.
You would want to have him.
You're listening to Skeptically Speaking. I'm here with Samuel Arbesman, author of The Half-Life of Facts: How Everything We Know Has an Expiration Date. So you mentioned this idea that we tend to learn these mesofacts when we're young and not necessarily realize that they've changed. And you give examples of how parenting often is one of the main reasons where we butt up against the new knowledge and find out from our kids. If that's the case, that these are always changing, how do we know that our new ones are better than the ones our parents had and the ones their parents had?
This is actually a great question. Because I think for a lot of people, when they see this flux in knowledge, they often just throw their hands up in despair and say, oh, I guess it's always changing. And so therefore, we're never really going to know what's true or what's not. And then they kind of just tune all this flux out, which is a real problem. And I think overall, we are getting closer and closer to a true understanding of the universe. And actually, Isaac Asimov, he made this point really well when he was talking about changes in how we viewed the shape of the Earth over time. And so he said, when people thought the Earth was flat, they were wrong. When people thought the Earth was spherical, they were wrong. But if you think that thinking the Earth is spherical is just as wrong as thinking the Earth is flat, then your view is wronger than both of them put together. The world is not actually a perfect sphere. It's a type of geometric object known as an oblate spheroid. But the perfectly spherical view of the world is a lot better view of the actual shape of the Earth than a completely flat Earth worldview. And you can actually look at it in terms of the amount of like curvature per mile that each view of the world implies. And you can see that we're getting closer and closer. And I think this is the way to view science. Yes, it might be true that we're overturning various bits of knowledge, but often these kinds of things are occurring at the frontier of knowledge. This is where we know the least, but where a lot of really cool things are happening. And so there's going to be a lot of flux and a lot of noise at the frontier. But as time passes, we get closer and closer to understanding whether or not it's the actual shape of the world or just how the world works and how the universe works and the shape of the universe. And I think we're getting closer. And I think people need to recognize that beneath all of this flux, not only are there regularities to how knowledge grows and changes, but there are also regularities in how we're approaching a better explanation for how the world really works.
I think you use another analogy of like an asymptote. So something
Yes.
that we're just getting closer and closer and closer to.
Yeah, and within mathematics, you have this idea of like the asymptote, where it's a curve kind of constantly approaching something, and maybe it's never quite getting to the actual value, but it's getting closer and closer, and essentially infinitely closer over time. And I think that might be the way to view the scientific process. I mean, we're probably never going to have an exact view of everything. And this is why scientists continue to work, because there's always new things to learn. But we're getting closer. That being said, within the philosophy of science, there's something known as the pessimistic meta-induction, which is the idea that, yes, we think we're getting closer, but guess what? So is every previous generation. Every previous generation has thought we've had a really good understanding of the universe, and then we've totally overturned everything. So we need to be at least a little skeptical and recognize that, yes, I mean, there might be new advances, but at the same time, oftentimes those overturnings have included everything that we thought we knew as a special case. So, like, for example, when Einstein developed his theory of gravity and how the world works, Newtonian mechanics wasn't just thrown out, it was subsumed within Einsteinian mechanics. And there are many cases where an Einsteinian view of the world is a more precise view and actually works really well. But when you're trying to figure out where a cannonball will go, you don't really need to include general relativity in that. And the Newtonian mechanics gets the job done.
Yes, very well. So maybe the problem isn't so much that we aren't getting closer, but maybe sometimes we just misunderstand where we are on the curve.
I think so. And the truth is, in some cases, we still don't know. We really might not have a good sense. But I think in other cases, we have a pretty good sense that we are getting closer. And if you just look at previous generations and previous centuries, we're orders of magnitude better in terms of understanding the universe. And so for certain things, I mean, we understand like the fundamental laws of physics at like everyday energies and everyday temperatures really, really well. We pretty much understand that entirely. That being said, when you begin to go at like higher levels of complexity, things like understanding fluid dynamics or understanding biology or understanding how societies interact, there's still a lot we don't understand, but we've made quite a bit of progress.
One of the things that I found really interesting, I mean, as I say, we have made a lot of so much progress in those areas and have a really great understanding, especially at exactly everyday energies and speeds and masses and things like that. But I found it really interesting that we often hear this idea that right now we really live in the time of the most change, the greatest change. But you seem to actually talk about the fact if we really are thinking of this as an exponential curve or something similar to that, every time period before us was also the period of greatest change.
If you're thinking about it in terms of exponential change, I mean, exponential change is essentially, rather than constant growth, it's a constant rate of growth. And so in that sense, at every period before that, it was the fastest ever. Now it's continuing, and the amount of change is much more than before. So yeah, I think we've always had these periods of phenomenal growth, and maybe it's speeding up now. I think one of the ways to think about this, and it could be that maybe things are speeding up such that we now are actually able to see this change on the order of a single lifetime. So there's a paper about looking at urban dynamics and how cities grow over time. And within this paper, they look at they create this simple little model to show how cities grow. And within the model pretty much implies that after a certain amount of time, you're going to have like infinite growth, or you're going to have some singularity essentially in the model that can't be accounted for in the real world. And so you need to like reset the parameters. And these parameter resets, they equate with sort of like massive innovations, such as developing sanitation systems to allow cities to grow better and better and higher and become more dense. And the interesting thing in their model, though, is they show that these resets, these innovative resets, need to occur more and more quickly. And only recently have we gotten to the point where these innovative resets are occurring multiple times within a single lifetime. And so in that sense, and maybe this might only be a single case, in that sense, innovations, and we have to deal with innovation in a very different way and change in a different way than we have in previous centuries or previous generations. And so things do feel different. That being said, I mean, as humans, we're extremely resilient and adaptable to change. And we deal with huge amounts of information and much more information than we've ever had to deal with. But one of the ways we deal with it really well is we just tune a lot of it out. The question is, then the question becomes, how can you tune a lot of it out so you're not overwhelmed, while at the same time making sure that the important information filters through to you? And that's an open question. We're still trying to figure all of that out. But I definitely think, on the one hand, yeah, and things kind of are the same as they've always been. On the other hand, though, in terms of like certain ways of thinking about it, on the other hand, though, uh, we're dealing with questions that are and situations that are far different than what people had to deal with maybe like 100 years ago or even further out.
Especially, that would be a really big change between seeing one of these changes in a lifetime to seeing multiple of them in a lifetime. Even if kind of mathematically the rate of change of increase is the same, that would feel very different to a human being, I would imagine.
Yeah, and I still think we're still trying to figure that out. We're living in an exciting time. I think that's the most we can say.
And that's pretty cool. We'll be right back to chat more about the changing nature of the scientific world.
Skeptically Speaking is rebroadcast on a number of fine radio stations. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm Marie-Claire Shanahan, guest host today for Desiree Schell. Today I'm chatting with Samuel Arbesman, author of The Half-Life of Facts, How Everything We Know Has an Expiration Date. Samuel is an applied mathematician and network scientist who works to explore all areas of our lives through mathematical modeling. He is a blogger and contributor for Wired.com. He's written about math and science for the New York Times, The Atlantic, and the Boston Globe. So we were just talking about how we live in very exciting times. We often think of that in particular with relation to science and technology. I think that's where we can see so much innovation very directly in our everyday lives. But a couple of points in the book, you mentioned the fact that these regular patterns don't just apply in science and technology. Can you give some examples of other areas that similar models might apply?
When it comes to understanding knowledge change, we look at technology and science as kind of the clearest ones, and also they're probably the ones that have been most quantified, but you can look at more broadly at cultural innovation and items of cultural change. And so people have actually looked at the rate at which operas have been created over time and found that this also fits a roughly exponential curve of growth. And you can look at the amount of time it takes to double the amount of grand operas during this time when operas were being created. And I believe actually the doubling rate is significantly faster than certain areas of science and technology, possibly due to the fact that in science and technology, they're limited. While operas clearly have forms that they need to be structured within, they're less beholden to rules than, for example, science and technology, which are subjected to reality. And so therefore, to actually grow the number of papers or grow the changes in technology, you still have to actually query nature versus grand opera or other forms of writing. You can just be much more creative in a very different sort of way. In addition, people have actually looked at the rate that I believe fashion has changed over time and found that back in the Middle Ages, I think it changed maybe 50 years or so. I don't remember the exact numbers. Now it's actually sped up, and I think some people say it maybe changes on the order of every decade. And of course, there's many people who talk about last year's fashion and things like that. But so in some ways, going back to what we were discussing before, even cultural items are changing much, much more rapidly. So not only is it what we know and the technological items we're using, whether it's the iPhone or how we store information, these things are changing very rapidly. But also even, culture, elements of culture such as fashion or other. The number of books is growing quite rapidly. Then again, this was this was predicted thousands of years ago in Ecclesiastes, when in Ecclesiastes it says there is no end to the making of books. So even though things are growing much, much more rapidly now, I think we've always kind of recognized that whether it's culture or science and technology, these things have always been changing a lot.
And I guess especially if we allow ebooks to count in there as well.
Oh yeah, then it's off the charts.
One of my, I think, new favorite terms that you used was actuarial escape velocity. Can you tell me a bit about what it means in this context?
If you look at the lifespan of people over time, of humans over time, it turns out the average lifespan, the expected lifespan of humans has been growing over time. And this is for many reasons. We've been lowering the rate of infant mortality. We've had improvements in public health and hygiene and various basic things. And there are some people who argue that if you look at the expected lifespan over time, not only is it going to grow, but that maybe the rate at which it's growing is also increasing. So right now we might be, I don't remember the exact numbers, but maybe we're adding a month of life to people on average per year, which is great. So that means people are going to live longer and longer. But if we begin to add more lifespan per year every year, so maybe eventually it'll be half a year of lifespan per year that we're adding to it. Eventually, at some point, according to this argument, we might eventually reach the point where we're adding 1 year of lifespan per year. And so at that point, even though we might not have technology to make people immortal, that rate of growth means effectively that people are effectively immortal. And so at that point, when we hit the adding 1 year per year of lifespan, that is called actuarial escape velocity. And whether or not you buy into this argument or not, it's just this interesting idea that small changes, this kind of seemingly small changes and shifts in increasing lifespan, eventually there will be this tiny shift that can cause a fundamental change in humanity itself. In this case, going from being mortal, maybe long-lived but mortal, to being effectively immortal. And that's pretty crazy. So whether or not it actually happens, that's a separate question. But showing that, and maybe through this sort of interesting mathematical argument, that you can have a small shift that would create a big change for society is pretty cool.
Yeah, it is. Actually, and you use kind of an analogy of phase changes, right? Or even kind of a small change in temperature sometimes, if it's the right change in temperature, can have a really, really big effect on a substance. Do we see that in other innovations as well?
I think so. And so I try to use the analogy with phase changes, going from solid to liquid. Like when you raise the temperature a little bit and suddenly instead of going from colder ice to a little bit warmer ice, you actually go from ice to water, or going the other way, you're going from like different temperature water to an actual different substance to a different phase. You can see this in knowledge. So as small continuous changes in what we know or what we're able to do technologically, as these shift, these things kind of often following these exponential growth or various other regularities, as these things change slowly, we can often actually have a big change in what we're able to do or what we know about the world. So for example, there was a graph that was put out by the Air Force, I believe this was in the 50s, where they were looking at the maximum speed that we could achieve over time. And it was this fairly smooth curve, like going and like looking at cars and various other technologies. And it found that on this fairly smooth curve, eventually, and they predicted within a few years of the chart that they wrote, you would be able to create satellites. You would be able to have things that actually orbit the Earth. And then 1957, we had Sputnik. This is a big phase change in what we could do technologically, but it actually was predicted by this underlying smooth curve of change, similar to the smooth temperature change, with that actually can still yield pretty stark phase changes. And you can actually see this in other areas, and I looked into this in terms of how you could look at the discoveries of extrasolar planets, and like looking at the size and shape and the distance of these planets from their suns, from their stars, to see whether or not these discoveries could actually yield a smooth curve towards a fundamental shift in what we know, in this case, the first potentially Earth-like planet that would be discovered outside the solar system. And we were able to do some little math and actually predict that it would actually be quite soon. And as the Kepler mission is showing, we are discovering these increasingly Earth-like planets every day.
Yeah, that's something that's been a huge change in what we know about the universe.
And now we know about potentially Earth-like planets. We now have a much better sense of the different types of planets that orbit different stars. But really, I mean, until less than 20 years ago, we didn't know about any planet outside the solar system that orbited a sort of sun-like star. And actually, if you go back and you watch Cosmos by Carl Sagan, the documentary series, he talks about the various ways in which you could detect these extrasolar planets, but it was still purely hypothetical at that point. But he said in this one scene, he's talking to a room full of school children and says, in your lifetime, these planets are going to be discovered. And he was right. And we did it, but it was this fundamental shift. And we've undergone a lot of these fundamental shifts, even though in retrospect, sometimes it's hard to predict them going forward. These things can often be described and understood in terms of fairly smooth changes, whether in scientific knowledge or technological change.
Funny enough, I actually just watched that episode a couple weeks ago. So as soon as you mentioned it in the book, I had a big smile and knew exactly what you were talking about.
Oh, that's great.
You're listening to Skeptically Speaking. I'm here with Samuel Arbesman, author of The Half-Life of Facts, How Everything We Know Has an Expiration Date. Okay, if you'll allow me for a sec, I think the middle school teacher in me has to ask you this. So thinking about that phase change idea, one of the things we often do with students in sometimes their very first chemistry classes is have them plot heating and cooling curves. So same thing, they measure the temperature of ice and watch how there's just slow changes in the temperature of the ice. But then at a certain point, we're still transferring a lot of energy into the system. The beaker with the ice in it is still sitting on the hot plate, but the temperature isn't rising anymore.
Right.
And it gets this kind of plateau before the phase change happens, or just as the phase change is happening. I couldn't help but wonder if there was any piece of the analogy that sort of works to that when those big things are happening. Are we, in a way, putting a whole bunch of energy in that for a little while isn't getting us anywhere until that breakthrough? Or have I totally pushed the analogy too far and broken it?
I don't think you've broken it. I don't have any math in terms of understanding knowledge and technology, but I think there's something there where oftentimes there's this period where we have maybe some goal kind of in the far off distance, and then for a little while we view it as far off in the distance and we're never going to get there, and suddenly we do. And so maybe we put a lot of effort and it seems like we're never going to get there, and then suddenly we have this breakthrough. So there might be something there. I don't have any specific examples to kind of back it up, but we definitely, I mean, there are certain cases. I think I talk about the iPhone in the book, where, I mean, the iPhone, it was combining pre-existing technologies, but when it came out, and it felt like it was from the future, and some people didn't even believe it could exist because it was just so new. And so I feel like there are sometimes, even though, I mean, there are a lot of things happening, and there's a lot of energy being exerted in underlying technologies, and then suddenly everything is put together, and then we yield something new. And so maybe that's the way to kind of push the analogy further. I don't know if that quite gets at what you're saying, but yeah, I definitely think there's something there.
Well, thanks for indulging my analogy pushing. So I really enjoyed the sections of the book where you kind of brought and shared some of your personal experiences of bumping up against these patterns. We talked a little bit about the Brontosaurus and how something a lot of us learned about when we were kids. Are there any other examples where you've sort of brushed up against this idea of really changing knowledge in your own mind that stand out to you?
One example, maybe it's not my own life, it's in life of people in my family. I actually begin the book with this, is my grandfather. So my grandfather, he turned 95 last summer. And when I was working on this book, I would talk to him and he would just give me example after example of things that he learned that are just so wrong and so bizarre, or just he'll tell me about the vast amount of technological change that has occurred in his lifetime. He's a retired dentist. And when he was in dental school back in, I guess, the late 1930s, he learned the wrong number of human chromosomes. And so we now know that the number of human chromosomes there's 46 in each cell, 23 pairs. But there was a period of several decades where this number had been counted incorrectly, and people thought there were 48 instead of 46. And this number was propagated in all the textbooks. People thought it was kind of a done deal. And it wasn't until the mid-1950s that people used better biomedical technologies to actually visualization technologies and realized that this number was wrong. And there's just like so many examples of this kind of thing where we bump up against change. And my grandfather, he has tons of these, and it's been wonderful to kind of talk to him about this.
My favorite that kept coming to mind was my mother and I were both lifeguards, trained many decades apart, and she still had all of her old manuals. And in it were the instructions for doing artificial respiration by pumping the person's arms back and forth above their head.
Huh.
And I was just shocked that would seem like a good idea to anyone. But
that's so interesting.
She when I first mentioned it to her, she's like, "Oh, they don't do that anymore." But just because she had never trained after that and never bothered to, or had never come up against the fact that was something that wasn't really a great idea.
Wow. Well, so I know a lot of my family are actually in like the medical fields or the dental fields, and so from a young age I've seen both knowledge changing, but also how they've had to engage in continuing medical education or various other ways of making sure they have things that are more up to date. Because in every specialty you want to make sure you're up to date, but in medicine, lives are on the line, and so they really have to figure out how to do this. That being said, a lot of people are still out of date when it comes to certain bits of knowledge. But yeah, you really have to try hard. And in the field of science, a professor of mine from graduate school, he actually told me this great story where he went into his class to lecture. It was on a Tuesday and gave his lecture on a certain topic. And then on Wednesday, the very next day, he read a paper that actually invalidated what he had taught the day before. And so
Oh,
he went
wow.
in. Yeah, so on Thursday, then he went into his class and he said, "Remember what I told you on Tuesday? It's wrong. And if that bothers you, though, get out of science." And so he really encapsulated this idea that, like, yes, science is changing. The one unchanging thing is the process, is the recognition that knowledge is in a draft form, and we use this process of querying nature and really to really understand the world. And when he told me the story, it was amazing. I loved it.
That is a fantastic story. Because that's a different story than I told you something that I thought was true but wasn't. Is really different from, in a sense, it was true to every piece of information that he had that was good information up to that point. But
Right.
there was now new information.
Right. And rather than kind of saying, "Oh, we were wrong," or kind of brushing it under the rug, he reveled in it. He's like,
Hmm.
"This is the beauty of science." And I think this is why a lot of scientists work at the frontier. It's where we don't know exactly what's going on and where things are going to be overturned. But that's part of the process. That's the excitement in being able to make discovery.
So it seems to me there's a big message in this is that in this kind of world of scientific information, things can be constantly changing, but it doesn't necessarily have to be like a dizzying whirlwind that doesn't really mean anything. Why do you think that's really important for people to know?
By recognizing some of these regularities behind all of these changes, people recognize will first understand how knowledge grows and changes. I think that's an important thing. I think it's also important to recognize that that's often more important than simply just memorizing facts. And when we're in school, we learn a lot of bits of information that are then outdated fairly soon after. I mean, in medical school, they teach you that a large fraction of what you learn, they tell you this explicitly, that a large fraction of what you learn is going to become obsolete within like a few years of graduation. And I think we need to begin internalizing this idea that it's not as much what you learn, but also how you learn, how you constantly learn, but also how you recognize the patterns and how knowledge grows and changes. And I think if we can internalize this, if we can see how science and technology change, the rules and the order behind that, then we'll have a better appreciation when we read the news or when we think about public policy or even how we deal with children's textbooks and like the differences between our kids' textbooks and our own. It won't be as dizzying. We'll actually recognize that like it shouldn't be worrying. That like we don't have to be worried about this change. We can actually embrace it and say, this is how the world works. This is really exciting. This is a lot of fun. And we can actually embrace all these changing facts because we'll be better prepared to deal with them.
And that actually is pretty exciting. You talk about one other thing that I think maybe isn't a fear that people outside of science necessarily have, but probably something that a lot of scientists do fear, which is discovering something that someone else has already discovered or come up with. And it seems like it's not as rare as one might think, and seems to actually happen even to good scientists and happens in different fields. The pattern gets repeated. Should they worry any less about this?
As science grows, and it's growing incredibly rapidly, no single human being can read all of science, let alone even sometimes your own subfield. And so this kind of thing is going to happen more and more as science becomes specialized and as science grows. And you're going to end up recapitulating things that you think are novel but have been done by someone maybe decades ago or someone within a few years of you but in a totally different field using different jargon. And so therefore you don't actually know that it's been done until someone realizes, oh, wait a second, this is the same thing just with different terms. You want to try to look in the literature as best you can and make sure that things
Of
are not
course.
being done and you want to do your due diligence. But I think this is not, it's not a bad thing. But I think the flip side though is we need to begin to incentivize scientists to actually be able to bridge one field to another. And I think, and we talk a lot about increasing the role for interdisciplinary science and interdisciplinary research, connecting different fields. And I think we need to recognize this is really, really important because we need people to run essentially this import-export business of saying, okay, here's a really good idea in one field. Let's take it and apply it in another field rather than that other field reinventing it. And we're getting there. And I think people are recognizing that a lot of really cool things are happening at this sort of the boundaries of different fields. But yeah, it's going to continue happening where people are going to recapitulate things, reinvent things that we thought were totally new. But if we can find ways of kind of bridging the jargon differences or bridging the different fields, hopefully we can reduce it, but also get different fields to talk to each other and make sure that the best ideas from each field are being applied to the other ones.
Cool. I spent last evening with a bunch of 17 and 18-year-old students who really want to be scientists. If there was sort of one thing that you could tell them based on the work that you do and based on the research that you did for this book, what would be something you would want them to take away?
And the story I told about my professor from grad school of like saying like how like things are going to be overturned, but this is really exciting. I think that's one of the most important messages in science, which is, and things are going to be overturned. Sometimes your own research is going to be overturned, but part of science is trying to get closer and closer to a true understanding of the universe. And if you enjoy the journey, a lot of stuff is going to change, but that's a lot of fun along the way, and revel in it.
That it's sort of the point.
Yeah, that's exactly the point is the process of science.
Thank you so much, Sam. It was really great to chat with you today.
Thank you. Thanks so much for having me.
You can find links to The Half-Life of Facts and Sam's other work on our website, skepticallyspeaking.com.
On the next episode of Skeptically Speaking, we're examining the scientific perspective on so-called psychic powers, like telepathy, telekinesis, and remote viewing. We'll speak to science author Brian Clegg about his new book, Extrasensory, The Science and Pseudoscience of Telepathy and Other Powers of the Mind. And we'll speak to Ricardo Lozano, researcher in non-invasive brain-computer interfaces, about experiments working on connecting different animals directly through their brains. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm guest host Marie-Claire Shanahan, here today for Desiree Schell. My next guest is Mark Daley. Mark is a lead researcher in the Brain and Mind Institute at Western University and an associate professor in the computer science and biology departments there. He uses computational modeling to study networks of all types, including biological and neurological systems. Welcome, Mark. It's great to chat with you today.
Thanks for the invitation to chat, Marie-Claire.
So tell me about how someone like you might find themselves working in both a biology and computer science department. Certainly the way we learn about them in school, those seem like really separate things.
Yeah, well, it's not a direct path, that's for sure. It's sort of a meandering one. I left high school thinking I wanted to be a professional jazz musician and pursued that initially and then realized, I'm kind of a nerd. Maybe I want to be a mathematician. And so I went back to school and did math and computer science and thought, this fits pretty well. And at some point, computation became kind of a metaphor for seeing the whole world. So you can take something simple like a cell. It's actually reasonably complex, but it's small. And the DNA inside that cell encodes a program that through a computation can grow an entire human being or an entire other organism. And so, that's a really interesting idea. We think of computation in terms of digital computers because those have been so successful, but really computation is just a process where information changes, transformation of information. So I got very interested in that and that whole idea of taking computation as this tool for viewing the world, the same way physicists use physics for viewing the world, and got interested in studying biological systems. And that started with cellular and molecular, and I guess at some point in all this thing, you realize if I'm interested in computation and natural things, the human brain's a pretty attractive target. So that's sort of the circuitous route I took to ending up where I am today.
So you said you got really interested in human brains, and I can see the connection there. Tell me a bit about some of the things that you study about the brain using your approaches.
Again, I'm interested in the brain as a natural computer, so a computing device that exists in nature. But that's a really broad kind of topic to study. So in particular, what I'm doing right now is using a branch of mathematics called graph theory, where it gives us a nice abstraction for reasoning about networks of things. And I'm going to start with a non-brain example. So Twitter is a really good example. You can imagine Twitter, each individual on Twitter, just draw a little circle for them. And then if someone sends a message to someone else, then you can draw a line between those two circles. You could do the same thing with your Facebook friends graph, right? If you're friends on Facebook, you draw a line between a circle representing the two people who are friends. So these create these lovely structures called graphs, which are a nice mathematical abstraction for talking about relationships between things. So how does this apply to brains? Well, the way it applies to brains is I want to look at various chunks of the human brain and understand how they communicate with each other. So this graph theory gives me a framework for talking about relationships between chunks of brain.
What kind of stuff can you learn about the brain from studying it that way?
All sorts of stuff. So certainly I'm not the only person doing this. This has been a fairly hot topic over the last 6 or 7 years, and there's kind of a whole army of mathematically inclined neuroscientists who are moving into this field. So it's a pretty profitable way to look at the brain. What I'm interested in particularly is communication between different brain areas during tasks and how that changes during different tasks. So again, if we go back to this simple model, if I've got two chunks of brain and they look like they're working together on a particular task, I'm going to draw a line between them. And then I can start building up these graph structures and ask questions about these graph structures. Like, in total, how many of these edges are there? Is there any kind of interesting structure? Do these edges have any particular interesting set of connections to them? Are there particular nodes, particular chunks that are really important? They're connected to everybody else. So by asking these types of questions, I can get some kind of understanding of what's going on in the brain. And if I'm interested in a clinical story here too, you can imagine that folks suffering from various types of psychiatric illness may have brains where these structures are quite different, and this could potentially be a diagnostic tool.
And so when you're talking, you use the word edges. Do you mean the lines connecting the two?
Yes, sorry.
Okay, no, that's all right.
So yeah, when I talk about the circles representing, people on Facebook or brain chunks, you might hear those called nodes in the scientific literature, and the edges are the lines we draw between those nodes or those chunks.
Showing the connections between the two.
Exactly.
Now, you've also mentioned that you studied gene assembly and genetic information as well. How does that fit into, I can kind of imagine how a brain is very networked. Is there something similar, or how do you approach looking at genes?
You can do all sorts of interesting networks with genes. So you can look at how different genes are expressed over time. So if you take a cell and you look at all the genes being expressed in that cell over a period of time, you might want to ask a question, okay, so are there any pairs of genes where their expression profiles really look like they're similar? So whenever this one gene starts being expressed, this other gene starts being expressed too. And when I say expressed, what I mean is the gene gets turned from the DNA code into a protein that actually goes and does something in the cell. So you can start looking at that in terms of networks. If two genes go up and down in expression together, well, let's draw an edge between them, and the genes are the nodes, or the little circles. And those graphs have been very profitably mined by biologists for at least 15 years now.
If someone had asked me to imagine something you could study with a network, I probably would have come up with brains eventually, but I really wouldn't have thought of genes and genetics.
And that's just the tip of the iceberg. You can also look at all sorts of other things. So I've had a couple of graduate students looking at how copy number variation changes across different individuals. So copy number variation is this idea that you don't actually have just one copy of a particular gene. You might have several, but that might change between different people. So again, this gives you another story where you can start to ask, how do these things co-vary, and can I build a network from it? And so it's one of these things where, everywhere you look, you see networks, especially if you study networks. So
everything starts to look like a network.
Yeah, I mean, you want to be careful, of course. You don't want to grab your hammer and go looking for nails. But I think that this is it's a really powerful abstraction, again, simply because it comes back to talking about things and relationships between things. And that's often something we study in science.
Is there anything else you think would surprise me that you can study from a network perspective?
I mean, here's something that might surprise you or not, depending on how much you've read up on this. You could create graphs studying how different jazz musicians interacted with each other over the last 60 years. So this is harder to do with rock musicians because bands tend to be, pretty tight and stick together. But jazz musicians, there's a real culture there of constantly playing out and switching up your group and playing with other musicians. And so you could create a chart of who's played with whom. And you build one of these graphs, and you'd be able to identify hub nodes like Miles Davis and Herbie Hancock, which are sort of household names in jazz. And these would be the people who would have lots of connections to lots of other people in that graph.
Cool. So it'd be another way of kind of looking at influences and who's been important. Would you get that kind of information out of it?
Absolutely. So it tells you who sort of the key members are of a community. So you could look at one of these graphs and say, if this person were to stop collaborating, this would be a real loss to the community. So another one that might be surprising is someone has done something similar here at Western with authors from the Spanish Baroque, where they're looking at relationships between Spanish Baroque authors. And this is just a good luck story where this particular grad student took a course I was teaching and thought, hey, I can apply this to my research. And so even in humanities, this extends way beyond science. This is, again, just a powerful tool for talking about relationships between things and how those relationships evolve.
Okay, you surprised me.
There we go. Okay.
Well done.
Hooray.
Those are really interesting examples. You're listening to Skeptically Speaking. I'm here with Mark Daley, an associate professor in computer science and biology at Western University. So you mentioned off the top a little bit that you have a music background, and you've given us a really nice jazz network example. Do you think that the fact that you're a musician first and a composer, do you think that plays into the way you see any of these questions at all?
I'm not sure if it does directly. I mean, people make a lot of this supposed connection between music and mathematics, and I don't know if that's a real thing or not because I haven't studied it scientifically. But I think what the music background gives me two things. One is an open mind towards approaching other disciplines. So one of the dangers with being a scientist and doing your PhD and your postdoc is you can get very narrow and very specialized. And by maintaining a network of friends doing totally different things, I think that helps to sort of keep me grounded and honest. And the other way it helps me is very pragmatic, is in performance. Whether you're lecturing to a class or giving a talk at a symposium, it's really important to be able to perform well. And having spent so much time on stage performing in my earlier life, it's a lot easier than if I didn't have that experience.
Have you yourself done any sort of computational work related to music at all?
I have done a little bit, sort of by accident. I had a graduate student, Jeff Smith, when I was at the University of Saskatchewan, who worked on computer-assisted composition. So we didn't want to do computer composition. There are certainly people who study that, totally computer-generated music. What we wanted were tools to help someone who was, intuitively musical and really wanted to compose but hadn't yet developed all of the theoretical and mechanical skills to help enable them to take that creativity and interest and turn it into music that hopefully sounds kind of good. And I think we were reasonably successful at doing that. So we came up with a whole software system and a nice user interface for helping people to, just jump in and start creating music.
How would a program really do that?
Well, by presenting things in terms of simple abstractions. So this particular program is called Real Song, which kind of gives you an idea about how it's structured. So you can imagine pieces of music are often based on repetition. Mm-hmm. And so if you take a core idea, a germ of music, and imagine it as a gear that's spinning, and then another melody or counter melody that would go along with that might be another gear that sort of interlocks with that. And so by taking that metaphor and pushing it, you can create a system where people can, sort of put these gears together. They have some idea of what they want. And then a lot of it becomes play something back for them and just ask, did you like that or not? And if they say no, try to recombine it in a new way and give them something fresh and until they find something they like, and then try to build on that success. By no means is this an easy undertaking. We certainly haven't solved the problem, but I think we made a baby step towards producing something that's at least fun for moderately musical people to play with.
Very cool. What would be the computational side of that?
The computational side of that is really generating algorithms that produce melodies that sound at least palatable. So you can't just do this as a totally random endeavor. You have to have some pre-knowledge of musical structure and form. And so how do you encode that into an algorithm that can produce a simple melody for the user to listen to that says, yeah, that's kind of what I wanted, and it sounds good.
I'd really like to try that sometime.
I can send you a link.
That would be very cool. So you've also done a little bit of work sort of showing how diversely this can be applied. You've done a little bit of work in languages as well. Is that right?
The work I've done is actually, it's in a branch of mathematics called formal language theory. So we're not studying natural language. We're studying the types of languages that a mathematician would use to describe mathematics. From a computational standpoint, what's interesting is formal language theory gives me a tool for reasoning about the limits of computation itself. So something that's not at all obvious if you haven't studied it is that there's a lot of things that you can't compute. And when I say can't compute, I don't mean that they're too hard or we need a bigger computer. I mean, you can prove mathematically that these things are impossible to compute ever. So one example of this is if I took a computer science student and said, I'd like you to write a program that will look at another student's program and tell me if that program is going to crash the computer or not. That's actually impossible. That's mathematically provably impossible to do. So formal language theory gives me the set of tools for reasoning what the actual limits are to computation. And then scaling that back, when I start looking at natural processes like networks in the brain, it gives me a framework for saying, so how complex is this network? What's the computational power of this network?
So in a sense, you're sort of studying the process of what you study?
Amongst other things, yes. But I think that the important message I wanted to get out is that it's an important tool for being able to put hard bounds on what computation means and what a particular computation is capable of.
So our show today really has been all about using computational and mathematical models to better understand things like how information spreads, how it changes, how it's communicated in our brains. Now you've given us Spanish Baroque literature and all kinds of things. What do you think is the overall value of trying to quantify and model almost anything?
The two big ones are the first are improved understanding. So if we can look at natural processes or artificial processes and model them as computations, as the spread or transformation of information, then that gives us some insight into how that thing functions. And if something is wrong with it, it might give us insights into how to fix it. And the other sort of nice branch to this that's complementary is it gives us means for creating reasonable simulations. So, I don't think we're quite at the point of simulating a human brain yet, but certainly you can imagine a simpler network simulation being something like the spread of a flu virus on a network model. That's already something that's used in applied public health, and it is very, very useful there. And that exists, that tool exists because we thought about the spread of viruses in terms of this sort of network model where it's something being transmitted over a set of connections between individuals.
And do you think these are insights that we couldn't get in any other way?
Well, that's a really loaded question. I'm not going to say yes because there's an infinite number of possible ways of sort of looking at the universe and studying things. And so undoubtedly, 200 years from now, some researcher will be, or a postdoc will be sitting in their office looking at one of my papers and saying, look how naive they were 200 years ago. This framework is clearly superior. But I think right now, it's the best we've got for studying relationships and how relationships change. And that's why network theory and graph theory are so popular right now, because people have realized, this is a really powerful tool for answering these types of questions, for modeling these types of systems.
So do you think I can add this to my answer that I sometimes give when kids ask me why they have to learn math?
Absolutely. My answer to that question is, math is a tool for helping you understand the world. And it's by far not the only one, but it's a very useful one, profitable one. So when kids ask, why should I learn math? Because it gives you power to understand your world, to model your world, and maybe even to predict your world.
Thanks so much, Mark. It's been really great to chat with you today. And that is a terrific lesson that I think even the youngest math students could learn from.
I hope so. Thank you for the invitation, Marie-Claire.
Oh, you're very, very welcome. You can find links to the fascinating work done by Samuel Arbesman and Mark Daley on our website at skepticallyspeaking.com. And while you're there, click the links to Facebook, Twitter, and Google+, so you can keep up with show news, and to iTunes, where you can subscribe to our program or listen to past episodes. Thanks for listening, and we'll see you next week on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.